This presentation is on the RSA cryptography algorithm and how and why it works. To aid in the understanding, I will run through this algorithm with examples. So, encryption is the standard method for making communication private. A person encrypts a message with a key, and only the intended recipient can decrypt the message. RSA is a crypto system where the encryption key is public and differs from the decryption key, which is kept a secret. RSA is based on the fact that factoring the product of two large primes is very difficult. So, as just an example, Bob wants to send Allison a message, and he translates the string into a bit representation and encrypts the message using Allison's public key into a cipher, and then sends the cipher to Allison. And Allison recovers the original message using her private key. So I'll just give an overview of the algorithm before I delve deeper into it. So the first step is when a user generates two random values and tests the primality of those values. A totient is calculated as the product of the primes. Since factoring the product of two primes is a difficult problem, an eavesdropper cannot determine the totient, and determining the totient will help us eventually discover the private key. Our public key is created based on our knowledge of the totient, and our private key is generated as the inverse of the public key. The encryption and decryption functions let us use the public key and private key to encrypt a message and decrypt a cipher. So the first part of the RSA algorithm is key generation, where the goal is to generate public and private keys. In order to ensure that safe keys are generated, we pick a random large number and test its primality using the Rabin-Miller primality tester. So how does this test work? Let us try to find out if 13 is a prime number. So in the first step, given n minus 1 equals 2 to the k times n, we want to find integer values of k and m that satisfy this equation. So starting from k equals 1, plug in their values, k equals 2, and in k equals 3, we stop since we are looking for integer values. So we determine our k and our m. In step 2, we pick a value a such that a falls between 1 and n minus 1. Let's pick a equals 2. In step 3, given equation b0 equals a to the m mod n, and plug in the values that we have, if b0 is positive or negative 1, then we can determine that n is probably a prime number. In this case, however, our b0 was 8, so let us continue looking at finding the equation for b1. So b sub 1 equals b sub 0 squared mod n, and calculating that value, we get negative 1. So if b sub 1 is positive, then n is composite. If it's negative 1, then n is prime, so we can determine that 13 is probably a prime number. However, we must remember that the Rabin-Miller is a probabilistic test. So in order to ensure that we don't get a false positive, the test is performed many times so that a number has a very small chance of not being prime. The next part of our algorithm is calculating the totient, where the totient is 1 minus p minus 1 times q minus 1, where p and q were our prime numbers. So given p equals 11 and q equals 13, our totient is 120. So RSA's security is dependent upon the fact that the product of two large prime numbers yields a composite number. But just given n, there is no n, which is p times q, there is no efficient algorithm to determine n's prime factors. If one can somehow find the prime factors of n, then it is really easy to calculate the totient, which is p minus 1 times q minus 1. With the totient available to you, calculating the private key is very simple, as we will see. Our public key is represented by the letter E, and it's a prime number that has a GCD of 1 with our totient. Let us say E equals 7, given that our totient was calculated to be 120. Now we can determine our private key. We know that the private key is a multiplicative inverse of the public key. How do we find the multiplicative inverse? Well, we use the extended Euclidean algorithm. That says that for any positive integers a and b, the extended Euclidean algorithm returns integers x and y such that it satisfies ax plus by equals 1. By taking the modulus b of both sides of this, we can reduce this. We can say that this is equivalent to ax is equivalent to 1 mod b. The fundamental RSA equation is the product of the public key and the private key is equal to 1 modulus phi. This is essentially modular multiplication with inverses. So, given that our public key was E, which equals 7, and our totient is 120, the GCD of E and our totient we first have to use Euclid's algorithm, where the GCD of two integers can be found by repeated application of division algorithm. So what we do is essentially repeatedly rewrite the GCD of 120, 7 as the GCD of 7, 1, eventually finding out that the GCD is 1 between those two numbers. Now we use the extended Euclidean algorithm, which is ax plus by equals 1. We essentially we use the equations that we have found in Euclid's algorithm and rewrite it as a format of 1 equals ax plus by. So essentially we just use this line and say 1 equals 1 times the product of 120 minus 7 times 17. In this case, there's no back-step substitution involved, since our numbers are fairly easy and our Euclidean algorithm did not involve many steps. So we reduce both sides by modulus of 120. And that gives us the inverse of 7 times mod 120 is equal to negative 17 mod 20. And given that we have our fundamental RSA equation, which is the product of E times D equals 1 mod totient, we can solve for D is 103. The last part of the algorithm is the encryption and decryption function. This is the RSA function for message M and key K. Essentially, these functions were generated as such since the RSA uses a trapdoor one-way function, which is that there's some secret information, which is the totient. Again, if we were given the totient, this would make RSA vulnerable. It would make the function easy to compute, since we could be able to compute the private key as the inverse of E mod totient. Then, given it some encrypted text, we would be able to find the original message. So basically, these functions were generated as such with keeping that in mind. So our encryption function is m to the e mod n. Given some message and some public key, we can generate a cipher text. So for example, given m equals 9, we can compute 9 to the 7 mod 143, where n is again the product of p times q, our randomly generated primes, to yield us some cipher text, and the decryption function is very similar, which is the cipher raised to the power of d, our private key, times modulus n equals m. So, so computing, we're able to see that we retrieve our original message back, which is 9. So let's talk about the property of the RSA algorithm, which is that if a message is to be encrypted, then the opposite key that was used to encrypt it must be used to decrypt it. This is such that given some encrypted text that's encrypted with a public key E, and given a private key, we can retrieve the original message, and vice versa. Given a message that was encrypted with a private key, and then given a public key, we can retrieve the original message. Well, we know our encryption function, as we stated before, is m to the e mod n, and then raised to some exponent d, which is our private key, is m to the ed mod n. And since multiplication is commutative, this can be rewritten as m times m to the power of de mod n, and then simply rewrite it as our decryption function, m to the d mod n, given some public key e. So essentially what we've found is either way works to retrieve our original message. Either we encrypt the message with a private key and then are given a public key, or vice versa. So let's understand why this encrypted text turns into a message when given the required key. So here we have our encrypted text E, encrypted function, and then given some private key D, rewrite the function as such, and then we know that E times D equals 1 mod phi, 1 mod detosant, which is the same thing as rewriting it as k times some constant k times detosant plus 1. And then we also know that the definition of totient, and we know Fermat's theorem, which says that m raised to the power of p minus 1 equals 1 mod p for any prime number. We can rewrite this function here that I'm underlining, given that we know the totient is the product of p and q, and given Fermat's theorem. So what we can essentially reduce it down to is saying that m to the power of ed mod n is the same thing as n mod p, and that it's also the same thing as m mod q. And we also know that p and q, the product of that is n. So what we found out that m to the ed mod n is the same thing as m mod n, which is the same thing as saying that given our encrypted text with some private key d, we can retrieve our original message m. So let's just review the steps of the algorithm one more time just to get a final understanding. The first part of the algorithm was to generate random prime numbers using their Rabin-Miller primality test. Again, the purpose of prime numbers is so that we can compute the product of the prime numbers results in our totient here. And the purpose of this is that factorizing the totient into finding out the primes is really hard. That way it ensures our RSA does not become vulnerable, and that our original message cannot be retrieved given our given the fundamental equation E times D equals 1 mod totient. So if the totient is known, we would be able to eventually recover the original message. Our public key is generated as the great GCD of 1 and our totient. Our private key is generated using extended Euclidean algorithm and inverses, where we use modular multiplication and this fundamental RSA equation. The encryption function is m to the e mod n equals c, where given some message and some public key e, we can generate a ciphertext. And then our decryption is given the ciphertext and some private key d, we can retrieve our original message. Thank you.